This one is pretty math heavy, so don't worry about it if you don't follow all of it. I did a big project that involved a lot of these equations, so I was pretty familiar with it to begin with. I found myself thinking recently about geostationary orbit, or more specifically, how you get there. I don't mean like how you actually physically get there with a rocket, what I mean is how you get to exactly the point on the Earth that you want to hover over. A geostationary satellite, for those who don't know, is one that doesn't appear to move at all with respect to the ground. If it's right above a certain point, it'll stay right above that certain point. But that brings an inherent problem. Once you're at geostationary altitude, you'll stay exactly where you are. You can't move. So how do you make sure that you're going to end up exactly where you want to be? As a quick aside, I'm leaving a lot of this to later me doing the visuals, since much of it is difficult to verbally explain and much easier to see. There is, of course, a general way to solve this problem, but before we get into that, I'll go on another little tangent. I found myself wondering if there were any orbital altitudes that had a natural synchronization when transitioning into a geostationary orbit. So my first goal was to find an altitude from which you could wait until your target zone was under you, and then burn to geosynchronous orbit and get there right as your target zone is passing under you again. The answer is sort of. You can do it, but you'll have to wait. See, no matter what you're going to do, you'll beat your target to geostationary altitude. But as long as you keep your orbit elliptical and you don't complete your geostationary orbit, you can just wait for 3 of these half orbits to finish, and by then you'll be fully lined up. This comes out to an orbital period of 16 hours, which means a starting altitude of 3,000 kilometers. So if you're cruising at 3,000 kilometers and you're willing to wait a little bit, it's easy. Just wait until your target is right below you. But that's not a very convenient orbit for us, so what if you're in a nice, easy, low Earth orbit to begin with, say 500 kilometers up? Well, the first thing we need to know is how long it's going to take to get up to the required altitude. This will be the whole equation for the period of an orbit divided by 2, since we're only going halfway around, which is given by this massive and terrifying equation, which you don't really have to worry about because it comes out to about 5 hours for our case. So now we know how long it'll take for us to get there. Now it's just a matter of timing. We need to make sure that we get to the point of our geostationary altitude right when our target zone is below us. Thankfully, we know how long it takes for the Earth to make one full rotation, 24 hours, more or less. Since we figured out that it'll take 5 hours to get up, we just need to find out how much the Earth will rotate in that time and adjust accordingly. 5 hours is 5/24ths of a full rotation because it's 5/24ths of a full day, or about 22%. 22% of 360 degrees is about 80 degrees, so that means we would have to make our first burn when our target zone is 80 degrees away from the opposite side of the Earth from us. The same approach can be used for any target altitude to begin with, and voila, you can now hover over any point on the Earth that you want.